So next up, what I want to do is I want to revisit an old example. We dropped I forget what it was, a baseball, a bowling ball, a coin, whatever, off the Empire State Building. And what we did before was we assumed that the only force, we know that all the forces are going to give us F equals ma. So here F is all the forces that we're considering. And what we did before was we know that, we considered the situation when the only force was due to gravity. What I want to do now is I want to add in air resistance. And so let's add in air resistance here. So this is worth mentioning here. And this is the force due to gravity. This is the force due to air resistance. So the R is for resistance. And what I want to do is, let's do it this way. So ma is going to be minus mg. We saw that the force due to gravity was just minus mg. So we talked about that before. And plus we want to come up with what's our air resistance. So we'll have to figure that out at the time. And we'll use a few different models. So let's do the same problem where we drop the ball or whatever you want to think about off the Empire State Building, but let's assume that the air resistance, F sub r, is proportional to the velocity that the ball is traveling. Okay, so this is one common assumption, is that you can assume that it's just proportional to the velocity that the ball is moving. So the faster the ball is moving, the more air resistance. That seems like a reasonable assumption. So we're going to assume that that's the air resistance. And so if we do that, I want to actually, before we go through and plug in any numbers, I want to develop what formula we're going to get here. And so if we do that, we're going to end up with ma is minus mg minus kv. K, by the way, is a positive constant. Okay, and so this tells us that A is going to be minus g minus k over m v. And this k over m constant is going to be all throughout what we talk about. So I'm just going to call that rho, just so we don't have to write k over m all the time. So rho is going to be this value, k over m. Notice that k is a constant and m is a constant, so rho is a constant. So A is minus G minus rho V. And this is a little bit different than what we had before, because before we had A was a constant, and then anti-differentiating gave us that our velocity was, this gave us that our velocity was linear, and then our position was quadratic. Here, though, this is a little bit harder because this is a differential equation that's now linear, because you can think of A as the derivative of V. So this A is really just dv dt. And then this is minus g minus rho v. And this differential equation is both separable and linear. So if you prefer to do one over the other, that's totally fine. I think I'd rather look at this as a linear equation. And so we would have dv dt plus rho, which is just a constant, times v equals minus g. And then our integrating factor, mu, is going to be e to the integral of rho dt. So that's e to the rho t. And so if we multiply both sides by e to the rho t, we're going to end up with e to the rho t plus rho e to the rho t times v. I forgot the dv dt before. So dv dt. And that's equal to minus g e to the rho t. And the left side is just the derivative of the product, e to the rho t times v. And that's the derivative of that with respect to t. So I'm just going to use a prime, since that should be clear we're differentiating with respect to t. And then to get rid of the derivative, we'll integrate both sides with respect to t. So we're going to get e to the rho t times v is equal to negative g over rho e to the rho t plus c. And we'll figure out what c is in a second. But now we can divide both sides by e to the rho t. And so this tells us that our velocity is going to be negative g over rho plus c e to the minus rho t. And this is going to tell us a few things. One is that we know that we called v naught the initial velocity. So this is the velocity at time t equals 0. And so if we plug in t equals 0, let's think about what's going to happen. This e to the 0 is going to go away, and we're going to end up with negative g over rho plus c. So we know that v naught is going to be negative g over rho plus c. Or in other words, c is going to be v naught plus g over rho. And so this tells you that your velocity is going to have the equation negative g over rho plus v naught plus g over rho e to the minus rho t. And I want to take a second to stop and think about this velocity equation, because this is definitely more involved than the equation that we've had previously, right? The equation we had previously was just linear. And with the linear equation, if you have a line, as t goes to infinity, the velocity will go to infinity or minus infinity, depending on the sign. In this case, when t goes to infinity, let's think about what's going to happen. If t goes to infinity, then e to the minus rho t is going to go to 0, because this is going to grow really big. It's going to be in the denominator because of the minus, and so that term is going to go away. And so it turns out that what's going to happen is when t goes to infinity, you're going to end up with just your velocity being this value. So this is worth writing down. So if we take the limit as t goes to infinity of your velocity v, you're going to end up with minus g over rho. And so this is what's called your terminal velocity. So this is the terminal velocity. So no matter how much time passes, your velocity is not going to end up going past that value, or it's going to, rather, I should say, it's going to asymptote at that value. Okay, so that is terminal velocity. And you can write, if you want, you can write your terminal velocity in the equation if you'd really like. So you're going to end up with the terminal velocity plus the initial minus the terminal velocity e to the minus rho t. Okay, so there's our equation. And then we'll integrate this one more time to figure out our position function. And our position function is going to be the antiderivative again with respect to t. This is a tau, by the way, so that's not t. So this is going to be t times your terminal velocity plus, let's see, if we anti-differentiate, we're going to end up with v naught minus the terminal velocity over negative rho e to the negative rho t plus another constant, which I'll call d. Okay, and so let's rewrite this just one more time before we solve for d. This is going to be t times your terminal velocity. I want to write this as your terminal velocity minus your initial velocity over rho. So I'm just going to interchange those at the cost of the negative sign plus d. And then we know that your initial position is going to be s of 0. And so if you plug in s equals 0, you'll end up with the first term goes away. The second term is going to be this v tau minus v naught over rho plus d. And so d, you can solve from here. D is going to be your initial position minus this quantity. Okay, this, by the way, is just getting the equation for the position, the velocity, and the acceleration. This is why earlier in your mathematical career, we just assume that there's no air resistance. Okay, air resistance makes this complicated, and this is the easier of the two cases that we're going to handle. So this is our value d. So all in general, our position is going to end up being s of t is going to be t times our terminal velocity plus the terminal velocity minus v naught over rho e to the minus rho t plus d, which is s naught minus this quantity. Okay, and there's our equation for S. I'm not going to bother to rewrite the equation for V, although here it is. And then our equation for A we had above. Okay, so our equation for A was there. And if we want, we figured out what V is, so we can go back and figure out how do we find A there. Okay, but we don't really need to do that. Okay, so this is what happens when the air resistance is proportional to the velocity that the object is traveling.